Hi, my name is DJ Huff, and it's February 21st, 2020, and I am in the Tuesday lab session at 1 p.m. with Alex Sample as my TA. Since my last video, there's been a little bit of crystal growth. There have been a couple smaller crystals that have formed on the bottom. The larger crystals haven't really changed much. They still remain the same size and have relatively same qualities. They're pretty transparent and clean cut still. There has been one change, as I've noticed a couple of the larger crystals have started to conjoin to form a larger crystalline structure. One change in the environment that could have affected the growth during this period would be a change in temperature. My room has been relatively cold lately since my roommate likes to keep his window open and the temperature has dropped over the past couple weeks. So this could affect the slow evaporation that we want. Otherwise, there's been no other changes to the environment. One thing that I would like to note is how much of the solution is actually evaporated. When we first began, we had basically a full vial of solution, but now we're about halfway. So obviously, there's been a decent amount of evaporation occurring. Now, if we wanted to create one giant, high-quality single crystal of alum, we would need to follow a process that's similar to the one that we did, but we would also need to add some things on. So if we wanted to create this high-quality single crystal of alum, we would need to create a seed crystal and use a supersaturated solution. So basically, we would form a seed crystal by dissolving a designated amount of alum, 4.56 grams for our lab, to create a saturated aqueous solution. Then allow this to sit for a couple days until there are crystals forming on the bottom, similar to our process. Now, from these crystals, you choose the crystal that has the desired characteristics. So the one that's preferably most clean cut, most transparent. You choose this one to be your seed crystal. Now that you have the seed crystal, you need to create a supersaturated solution by placing double the amount of alum in the water that you would normally place. So this would be, if we were doing this, it'd be 4.56 times 2. That's how many grams we would place in the solution. You will need to heat this solution so that all of the alum is dissolved. Then you would place the seed crystal in the solution and cover the solution with something to allow for slow evaporation and to reduce the temperature fluctuations. The crystal will now grow, forming off the seed crystal. This method was attained by the International Union of Crystallography. The first half of this method is very similar to our method, as we just formed a seed crystal. The second half of this method is the part that we didn't do, but we could do since we now have a vial full of seed crystals to choose from. We would just need to create a supersaturated solution with alum and place it in there, and it should form one large giant crystal. Moving on, D-spacing is the space between atoms in different planes of crystalline structures. X-ray diffraction can be used to determine D-spacing, and it gives us insight into the structure of the crystal. As seen by this picture, if these are all the atoms, D-spacing is just represented by the distance between them. Now, if we were looking at an X-ray diffraction graph, the D-spacing would be represented by the peak in the graph. So this would be the D-spacing here. We can calculate D-spacing using Bragg's law, which is just 2D sine theta equals n times the wavelength. The highest peak on the graph, like I said, is where the D-spacing can be measured. For our purposes, the highest peak on the graph would be 20.5. It occurs at 20.5 degrees. However, they measured this in 2 theta, so we need to divide by 2 to find our theta. So boom. The wavelength is given to us, and it's 0.15418 nanometers. And n is just an integer, and in this case, it is 1. So we combine all this to solve for d, and we get that d is 0.433 nanometers. So the D-spacing is 0.433 nanometers in the Alum. That's all I got for this week. Peace out, Alum.